On today's N is for Networking, we continue our introduction of Spanning Tree from last week's episode, which is episode 13. We're going to review a little bit, then cover Spanning Tree versions, guards, and filters, edge ports, and more. I am Ethan Banks, who's been doing networking since the 1990s, and with me is Holly Metlitsky, newer to networking, collecting certifications, and helping her customers buy the right things. And together, we navigate the modern networking landscape, helping you understand the technical fundamentals of moving packets around. You can find us on LinkedIn and the Packet Pushers community Slack group, which you can join free forever at packetpushers.net/community, and please do. Today's part 2 of Spanning Tree comes from a listener who said it would be great to go over Spanning Tree. It is a mysterious thing I don't fully grasp. BPDUs, root bridge, edge port, forwarding, blocking. When I've asked others to walk me through all this, the usual response is just to disable it. So Holly, we're gonna continue. What's funny is I thought originally this was one episode, right? And started working through all the material of the fundamentals of Spanning Tree for episode 1. I was like, oh, this is definitely 2 episodes. And now, worked on episode 2 for today of Spanning Tree. And maybe this is 3. Let's see how far we get today, Holly.
I know. It's a never-ending topic, but we will see how we go today. Hope you'll be good.
We will see how we go today. Let's start with some review, just to help people who have listened to the first episode could use a quick refresher. Spanning Tree is for loop prevention on Ethernet networks. Well, why do we need that? Because Ethernet frames don't have a time to live field. Time to live field meaning usually when a packet or a frame goes from one hop to another, the time to live field is decremented. And when the time to live field gets to 0, it's no longer forwarded. That frame or packet dies. Well, Ethernet frames don't have a TTL field, so they live forever. Ethernets use broadcasts frequently as a discovery mechanism. Hey, anybody out there on the wire know the answer to this question? That would be like a broadcast style question. And there's other reasons that broadcasts get used. So if we have a loop, broadcast frames accumulate and they never die, and that kills the network. There's just more and more broadcast frames as Ethernet uses these broadcast frames to solve different networking functions all the time. So Spanning Tree's purpose then is to discover the Ethernet network topology, how all the switches are plugged into each other, and then place links that would cause a loop into a blocking state. Does that sound right to you, Holly?
Yeah, I think that's mostly what we covered on the previous episode. And for those who maybe haven't listened to it, it's a good quick recap before we dive into the rest of it.
Okay, so a little more quick review then, as it was how Spanning Tree does this. Do you remember what the root bridge was, Holly?
So the root bridge is the designated switch that is managing the network, so to speak, or managing the system. So that's the designated root bridge that's chosen as the one with the lowest root ID. You are frowning. I am botching this.
I'm not frowning. That's harsh. Well, the only thing I was thinking was, the root bridge doesn't, I wouldn't say it manages the network as such, because there are devices in certain network protocols and different functions where you have a device that's kind of like the brain telling other people what to do. And I wouldn't put the root bridge quite that way, but it is the one that becomes the central figure in a Spanning Tree topology. That's how I would think of the root bridge. And everyone agrees on who the root bridge is based on what you were just describing. Root bridges, or all bridges in a Spanning Tree topology, get a priority, and the lowest priority switch becomes the root bridge. Now, we said switch and we said bridge. And for our purposes, those are the same thing. Are you remembering that?
Yes.
Yes, okay.
That much for sure.
Okay. So the root bridge is really important in the Spanning Tree topology. There's going to be an election that goes on, and that there's a bunch of different ways that the switches can determine who the root bridge is. Primarily, it's priority. The lowest one wins, but there are tiebreakers for different things that can happen in the Spanning Tree topology discovery process. So again, the lowest root bridge, which is the lowest root bridge ID, the priority, plus the MAC address of the bridge forms the full bridge ID. That's your root bridge. If there's other needs for a tiebreaker, like I have two links back to the root bridge, so the cost is identical. They both look even to me. How do I pick which one of them is going to be the link I forward and which one is going to be the link upon which I block? You could, depending on what kind of a tiebreaker it is, and there's various tiebreakers you might have, you could have two different root bridge priorities. What happens if they're both 32,768 or whatever the value is, some identical value. Um, you could have the lowest sender bridge ID might be a tiebreaker, depending on what the tie is you're trying to break. The lowest sender port ID could be a tiebreaker. Again, I'm at switch A, switch B, two cables in between them. Which one's the going to be the forwarding port, and which one's going to be the blocking port? Well, what are the differentiators? Because everything's identical. The two switches are identical. Everything. Okay. Well, the ports are different, and every port in a switch has an ID, and that ID could be part of the tiebreaker. The port ID is composed of the port priority, which is a value that you can set. If you get into the port interface, you can actually set a value on it. I think by default, this could vary by manufacturer, but my memory is, at least in Cisco land, the default port priority is 128, but you could adjust that. And then every port also has a port index, which if you've gotten into SNMP at all, Simple Network Management Protocol, Holly, but
Not much.
if you get into that, what you find is like, how do I query the statistics from a particular port? And there's going to be a port index number. They're all enumerated so that they're unique within the SNMP hierarchy. That index might be used as part of the port ID as well. And again, some of this stuff might vary by manufacturer and so on. All of that to say, the port ID could be a tiebreaker. That's really the thing I want us to remember. And honestly, for purposes of this level of podcast, it's like, I just want people to know there's tiebreakers and be like, oh, what happens if all the values are pretty much the same, if the costs are the same and the root bridge priorities are the same, or, et cetera. Well, there are tiebreaker mechanisms, and I hit some of them. But it would be up to you to dive in a little further and study out what those are if that's important to you. So, all right, now that was all by way of review for the most part. Hey, we're doing good. We're only 8 minutes in, Holly. We're doing good. We're doing good. All right. So I have a question for you.
Alrighty.
Yeah, I know you're looking at the notes too. Close your eyes. Don't look at the notes. Tell me what do you think happens if the spanning tree topology changes? By that I mean,
Yeah.
we got one link that was up and now it's down, or the root bridge switch collapses. It's no longer on the wire. What happens to the spanning tree?
Well, as spanning tree exists, it knows all of those things that happen, like all the ports, all the bridges, etc. So if you change something, it's going to have to send out a message and say, hey, something's
Yep.
wrong. This link's down. I need to fix
Mhm.
it. We need to do something to, I guess, converge the network again to figure out, okay, what is our new, for example, I don't know, if a forwarding port goes down, what's going to be the next forwarding port? How are we going to fix this? Which I guess would be used by BPDUs. They'd
Yeah.
send that out and someone would acknowledge it and say, okay, well, this is what we're going to do, and send that back out to the rest of the network.
Yeah, exactly. So BPDUs, bridge protocol data units, are the messages that spanning tree bridges use to communicate with each other about important things like their root bridge priorities and various other things. And one of the things that can be communicated in a BPDU is a topology change notification, a TCN. So that is a specific kind of bridge protocol data unit that gets sent out by a switch in the spanning tree domain when something's changed. Hey, something's different. Port went down, port came up, whatever it is. Something's different. Got to let everybody know. Oh, something's different. We might have a new topology, and so we got to think about this. Maybe we shouldn't be forwarding on the existing topology because something just changed. Maybe we've got a loop. We got to take an action here. So a BPDU with a TCN message gets sent towards the root bridge. When the root bridge finally receives a message that, hey, there's something's different on the network, it will reflect that. It's going to send back out its own normal BPDUs with the TCN flag. And the TCN flag, when all the other switches receive that BPDU from the root bridge with the TCN flag set, they're like, oh, something's different. Okay. And then a convergence event will happen. Now, when I say spanning tree convergence, what does that mean to you?
So that's figuring out the new network pretty much. So they've got to, I don't know why you'd really use the word converge, because to me that kind of means, I guess, coming together. So they're all coming together and saying, hey, this is the new network. For example, I don't know, a switch has gone down. We need to now all come together and figure out what route we're going to take instead of going through that broken
Yeah.
switch, for example.
Yeah, converge is used pretty commonly for a network topology change of whatever kind. We can use it in
Mm,
spanning tree. We might talk about it for a routing protocol. We would say, for example, global internet BGP never converges because there's so much churn on the global internet that BGP never settles into
mm.
a final state because it's always changing. And so it's always in a state of convergence. Um, and so spanning tree convergence event, what we're talking about is exactly what you said. Everyone's got to come to terms and agree, converge on what the new spanning tree looks like, what the new switch topology looks like, and then what the spanning tree should look like. And so these TCNs, topology change notifications that go out, notifying the root bridge that something's different, and the root bridge responding to let everybody know, oh, hey, something's different here, triggers this convergence event. So my next question, Holly, is why do we care about this? Is this interesting to us as network engineers beyond just, oh, spanning tree is going to like recalculate things and then reconverge on a new spanning tree?
Well, as something goes wrong in your network, you want to know how long is this going to affect your network for? Usually, that would be my instinctive reaction to, oh, switch down. How long is this going to take for us to converge and get a new route so my packets can keep flowing correctly?
And that is the key with spanning tree. You just nailed it. Because when a topology change happens, something is different now. Spanning tree, for to oversimplify it, is going to freak out. Oh crap! What if there's a loop? And so everybody that understands all the switches in the spanning tree domain that understand something's different are going to go back through the same process they went through when they were all booting up and discovering each other and figuring out who the root bridge was and who should my blocking port be and who should my forwarding ports be, et cetera. They're going to go through that process again. And while that happens, they're not forwarding traffic. And so if you introduce a new switch to the network, what will happen here is you're going to feel this for several seconds of the network not doing much of anything. Why aren't you forwarding traffic? And then everything goes back to normal again. You're going to feel it. You're going to feel it. Now, it doesn't mean the whole network feels it because you could have a bunch of different layer two domains, right? You could have a VLAN over here that's got its own spanning tree, and this other VLAN over here's got its spanning tree. And not every VLAN, not every group of switches affects every other one necessarily because they can be separated by a layer three boundary, a different section of the network, a different Ethernet effectively connected by a router. If you've got a router in the middle, that's where the edge of the spanning tree is. It stops at that border. So if you've got a network with 1,000 switches in it, but they're all separated by a bunch of routers, so really you've got like a bunch of little Ethernets interconnected. It doesn't mean a topology change in one part of the network is going to cause this spanning tree convergence event through all 1,000 switches. They're very likely going to have been separated by layer three by routed boundaries. But still, it is up to you as the network engineer to understand what is the extent of my spanning tree domain. If we add a new switch, that is going to cause a topology change to happen. What are the other switches that are a part of that spanning tree and how will they be affected? So that when you're planning like a change window, a maintenance window, you'll know there's going to be 30 seconds to a minute where the network hiccups. before it reconverges, it's settled back down. Spanning tree is like, okay, we're good, everything's stable, love it, let's go. Um, okay, so does that follow? Does that make sense? What questions have you got?
Yeah. No, I think that definitely makes sense. Um, I had a question and now it's just absolutely disappeared. It'll come back to me. We'll get
Okay,
back to it
got it. If you yeah, just interrupt me
if it
if
pops
that
back up.
question comes back to you. Yeah, yeah. Um, so okay, now how long the reconvergence event takes will depend on what version of spanning tree you're running. We're going to talk about that in a minute. But before we get there, I want to introduce some more terms that goes back to the person who asked that question. They asked about root bridge, edge port, and so on. And when we talk about things like an edge port and a root port, and there's a bunch of different, these are port roles, is what they're called. Every switch port that is a part of the spanning tree domain has a particular role that means something in the spanning tree sense. And so we want to talk through these now. Um, the first one is a root port. Do you know what a root port is? I don't know how much of this. I know you did some spanning tree stuff. I don't know how much of this you
I did
remember.
it. So when I read over the notes for this episode, I was reading because I used to get confused between root and designated port. I just don't know why, but they weren't explained to me very well. So after reading this, I was like, oh, it really clarified my understanding of it. So I never really had a good understanding of the root port. I just knew that it was in my head, it was kind of the main port on a non-root bridge switch. And then I read this
Yeah.
and I was like, that's not quite exactly what it is. Um,
Yeah. So you said designated port. So let's talk about these
yeah.
two kind of at the same time here. There's a root port and a designated port. Um, designate. I don't know why they called it designated exactly. I'd have to do some more reading to figure out why the word designated was chosen by spanning tree designers, or dig through one of Radia Perlman's books, probably the Interconnections book. I bet that it's kind of a networking classic. Radia Perlman's Interconnections probably has that information in there somewhere. So I don't know why the word designated specifically was chosen, because designated, we're designating something. What are we designating? I'm not sure. It seems like an odd choice of terms. So from the moment, but that is the spanning tree
Yeah.
nomenclature here: root port and designated port. So a root port is a port that is forwarding traffic towards the root bridge. A designated port is the opposite. It's traffic that is it is a port that is sending traffic away from the root bridge. Now, at first, that maybe doesn't overly clarify things, but let's walk through this. So, in a switch that's not the root bridge, someone else is the root bridge, and a switch upstream is going to be like, oh, my root bridge is, and he knows the port
Hmm.
priority and so on, and he knows via BPDUs where that switch lives. The closest path to the root bridge is via this port, and that is my root port, therefore. So I'm not the root bridge. The port on me that is the fastest path to my root bridge is my root port. So if I'm going to send traffic out that port, it's going towards the root bridge. You with me so far? Yes or no?
I am. Okay, finish the explanation, then maybe I'll get back to my. Maybe, no, actually, no, then I'll disappear from my head. But let's say, so that is your root port. So you're forwarding traffic towards the root bridge. Does
Hmm?
that traffic necessarily have to be um, going to the root bridge? Or can it go to a different switch along the path on the way to the root bridge? If that makes
It
sense.
could, the second thing, it could be
Okay.
going through, because your connection to your fastest path to root bridge could be through one or more other switches, depending on how you've laid the topology out. Yeah, absolutely. Now, you can have a spanning tree domain that's a whole mesh of interconnected switches. In a practical sense, as you build the network, you're probably not going to build it that way. For most networks, you're probably going to have a connection from one switch to the root bridge. It's going to be two layers, but you could have three layers. That's not uncommon. Um, but yeah, not to confuse it. Just saying, there's a what you can have versus what you're likely to see in the wild might be
Yeah.
different things. Is my point. But yeah, you can definitely be forwarding to the root bridge via yet another bridge that's not the root. It just
Hmm.
happens to be your path to get to the root. All right. So then a designated port is a port that is not, it's a forwarding port. You're going to send traffic through it, but it is not your fastest path to root bridge. That's your designated port. Okay. So if I'm the root bridge, Holly, do I have any root ports on me as the root bridge?
That is a good question. I'm going to go with a no because you don't have a port towards yourself.
Exactly right. Yeah. The root bridge does not have any root ports. The root bridge has all designated ports. And none of them are going to be blocking either, by the way. So we haven't talked about blocked ports yet, but yeah, if you look at the root bridge and you look at their what the port role is on the root bridge, everybody's designated. That's what it is. On a non-root bridge switch, you'll have a root port, and then you'll have one or more designated ports, and then potentially a blocking port as well. Okay, so then a blocked port. So what would the blocked port function for? What is its role?
So if you have, well, when you have multiple ports that could possibly be forwarding traffic, it's exactly, you don't want all of those forwarding traffic because that's how loops are created. So as we
Yep,
discussed previously, if you have, for example, in a basic situation, you've got two switches with a link, two links in between them, you've got to decide which port are you going to be forwarding traffic on and which is going to be blocked. Because if you have both that are forwarding, you've just got packets going round and round in circles.
exactly. So our blocked port is the one that is preventing the loop from happening. And we talked about this in the last episode where, yeah, it's physically plugged in, but it's not forwarding traffic. There's nothing being forwarded across that port. So here's another question for you, Holly. If I were to look at a diagram of the network, is the blocked port in a blocked state on both sides of the link? Like if I got switch A and switch B, and switch, let's say we got a triangle, switch A, B, and C. A is the root port, B and C are not the root ports.
Hmm.
So my connection between A and C and A and B, those are going to be lit because A is my root bridge. So between A and C,
Yes.
A and B, those are going to be forwarding. I'm going to have root ports and designated ports there. What about the link between B and C? That's where my loop is formed at that point. And so that's going to be my blocked link. So if I look at the ports on either end, I got a port on switch B and a port on switch C. Are both of those blocked?
That is a good question. I would say yes, because otherwise it's going to go and forward traffic but never get a response from the blocked port. But in theory, if only one is blocked, it's not going to have a loop. So,
You're thinking about it exactly correctly. So the answer is one side's going to be designated and the other side's going to be
yeah,
blocked. And I used to have this wrong in my head where I thought, oh, both sides are blocked, obviously, because it's a blocked link. I'm not gonna, both sides would be blocked, right? Well, no. What ends up happening is one side is designated and is forwarding traffic towards the other switch. In this case, our example was switch B and switch C. It depends on an election which side ends up being the blocked and which side ends up being the designated. But the designated port will forward traffic to the blocked port where it dies,
yeah.
and traffic never leaves the blocked port and goes to the other side. Are there exceptions to that with BPDUs? Like BPDUs might still go out. I'd have to check. There's someone who just studied spanning tree and is going, Banks, I can't believe you don't remember. Sorry, that's a nitpicky detail. It doesn't matter for our purposes in this conversation right now. But it was I just wanted to point out that, yeah, if you look at the spanning tree topology once it's settled and try to figure out blocked ports, you might think, oh, it's the whole link, both sides of it that go into a
Yeah.
blocked port role. Well, no, one side of that link will go into blocked. The other side will remain designated, and traffic will still get broadcast and so on and sent up towards that switch, even though it doesn't go any further than the blocked port. And the blocked port from the switch side where it is, he's not going to send traffic out his blocked port because it's blocked. That's where we've interrupted the loop so that we no longer have a loop. It's sort of an interesting detail.
Yeah, in theory, so we have this, say, triangle, and we have a blocked port. Now, the only link, I think it was A, whatever, call it A to C, is between, or the only, let's say, active link is from the root bridge to that switch. And the other link is between the two is blocked, right?
Okay. Yeah.
Now, if the link between the root bridge and whichever switch goes down, let's say the blocked
Hmm.
port switch goes down, I would assume that you would have to get BPDUs through that blocked port. Otherwise, you're not going to be able to connect that switch back to the root bridge.
Yeah, you will exactly, especially when there's been a change. We were talking about
Yeah.
topology changes earlier in TCN, so definitely a BPDU was going to go a TCN BPDU is
Yeah.
going to be sent out that blocked port for sure. What I'm trying to remember is, does a BPDU get sent from the blocked port out towards its neighbor switch? I think the answer is yes, but as a regular thing,
Hmm.
because they BPDUs do go out on a regular interval. It's one of those little details that as I spent time
Yeah.
reading and reviewing all of this stuff, I forgot to check. Anyway, don't get hung up on that if you're listening. It's not super critical for you to understand Spanish tree and what we're talking about at the moment. If you're a CCNA candidate, maybe you do want to dig into this, or JNCIA, maybe you want to dig into that and learn that. You probably do want to understand that in a more intimate detail. Get your Wireshark out and do a little studying. But all right, there's one more port mode that's important for us to get a hold of, Holly. So we talked about root, designated, blocked, and then edge is our fourth port role that I want us to cover. What is an edge port? Do you have a sense of an edge port? What that is?
Yeah. I, the only one that's kind of self-explanatory. Um, if you have an edge port, it is on the edge of your network. So it is not connecting back into your other switches. It is where your hosts will connect to. And I had a question. I remembered it, kept it in my mind. I didn't want to foreshadow the edge port. But if you have a switch that's on the edge of your network, let's say, is it possible for it to just have a root port and an edge port? Because it's either sending traffic back or it's sending traffic to a host. I don't know. I don't have a network topology existing in my brain
If
right
you
now.
don't if you don't have a physical loop that's
Yeah.
been cabled into the network, you're saying,
Yes.
then
So
nothing's going to be
it's,
blocked. Yeah.
yeah, it's
In
just
that case, you don't
going
have any block ports.
It's going straight back to the bridge, or it's going out to a host. No designated port.
No designated port.
I wonder if that's possible. You'd have to have like zero redundancy on that switch.
Yeah, there would be. Well,
Or
if you have on that switch some kind of like a port channel,
mm,
some
yes,
kind of ether channel group, all depending on the
yeah,
vendor and their nomenclature. Um, that bundle of cables appears to spanning tree like a single port, like
hmm,
or like a single, yeah, like a single
yeah,
port, and that's how it's treated. It's not treated as I have four links. If it's a bundle of four cables in the port channel group, let's say, it's treated as one group logically because it is. It
yeah,
relies on an underlying control protocol like LACP to keep that bundle straight and organized, and assumes that okay, so there's some protocol that's managing those four to act like one unified link, and so from a spanning tree perspective, I'm treating that like one port. So
yeah,
you'd have your redundancy, and there's no loop going to be introduced, and so in that case, now you got me wanting to fire up switches in the lab and just review. It's like, would we have designated ports? I don't, would we have in that simple topology that you were describing? I don't think so. I think we'd have edge ports facing out to all the hosts, and we'd have a root port going back to root in a very simple
yeah.
topology.
Which
And
is
why would we
similar
have a
to,
designated port if there's
yeah,
no loop in that scenario?
similar to our like triangle topology, you've got two switches just connected to the root. So you've got a root port and you've got a block port. But
Hmm.
one will have a this is where one will have a designated port and one
One
will
of
have
them
the
will.
blocked port. Yes.
Yes, and before we talk about Edge more, I forgot to mention this that to d- as the like in our triangle example, A was our root root bridge, B and C were the other ends of the triangle. So it's the link between B and C.
Hmm.
That's our redundant link. There is a spanning tree selection process that's going to go who should be blocked, who should be designated, which side is which. And there's a cost comparison that's done in there, and I forget exactly the what the cost comparison is on, and what tiebreakers might be employed, and so on. But there's a decision made based on numbers, effectively, which side is going to be the blocked one, and which side is going to be
Yeah.
the designated one. Oh yeah, okay. So edge ports, as you say, this is where the hosts plug in. There's not a switch that's supposed to get plugged into an edge port. An edge port is where our servers and printers and so on plug in. And it's so we're why do we call it an edge? Because we are literally at the edge of our spanning tree domain. Um, you might call an edge port an access port, depending on what vendor environment you're in. And an edge port, it's not like spanning tree knows this is an edge port and it's given a different priority or there's a flag set. It's not like that. Yeah, you can, depending on the network operating system, tell the switch this is an edge port, but it doesn't mean much to spanning tree as such. I think of an edge port. It's more like for network designers. They because we know that this is an edge port. I want this to function in a different way than all the other ports that might be interconnecting to other switches. And we're gonna talk about that a bit more in a minute here because we need to go through spanning tree states and stuff. I got some other points to make first,
I have
but
one more question on the edge
yeah,
ports
yeah, yeah.
before we run over. So you mentioned when you have like 1,000 switches, let's say you've got different broadcast domains, you've got different spanning trees with a router in between the two. Would the edge port be the port connecting to the router between the two spanning tree topologies? Because it's not a
Yep, that could
switch.
be an edge port. Yep,
Okay.
absolutely.
So not just
Absolutely.
host devices, could
Uh,
be
but I
routers or
just want to qualify that the port needs to be in a layer 3 mode,
yes.
because you can have switch virtual interfaces where it's actually a layer two port you're connected to that's participating in the spanning tree, but then you've configured a VLAN with an IP interface as your layer 3. So you do need to but as opposed to putting that port in router mode, in layer 3 mode, which is a different thing. You also
Yes.
might run into something called IRB, integrated routing and bridging ports, which are the same thing, where it is integrating both bridging functionality and routing functionality, and it would be participating in the spanning tree. So it gets fussy. You got to know what you're looking
Hmm.
at. But right, if you're connecting to a pure router, this is not a switch at all, or it's a switch with a port on it you've put into pure layer 3 mode, then is that an edge port? Yeah, that's an edge port. But just be careful that you understand exactly what you're doing there. And because this if it's truly an edge port, we're going to treat it like an edge port, and that means something. We're going before we talk about that, I just want to point out a few other things about spanning tree versions. We're going to stop here for today's episode. You will catch the rest of this discussion next week when we cover spanning tree versions, states, and guards. Thank you for listening to N is for Networking. Holly and I will chat with you again next week. More jargon, more concepts, and big ideas from the world of packets coming at you. If you have comments, questions, or a topic request, let us know at packetpushers.net/follow-up, and we will do our best for you. If you would like to connect with me or Holly, you can do so via LinkedIn or the Packet Pushers Community Slack group, which you can join for free at packetpushers.net/ community. And by the way, packetpushers.net has a ton of 100% free resources for you as you grow yourself as a network engineer. No login required. We offer a dozen podcast series that go as deep as you might want to get, including a huge backlog of thousands of episodes for you to search through. We've got weekly newsletters that help you keep up with what's going on at Packet Pushers and in networking. We have a YouTube channel that has demo videos and mini courses, plus our entire podcast lineup published as audiograms. Please share NS for networking with your colleagues. We would really appreciate that. And just remember, networking isn't hard. Other people figured it out, so you can too.